Hyperspace for space travel was a new concept that Giorgio came up with. Okay. So he starts out, since the beginning of science, time to be considered an independent variable, and I should be reading off this, which in practice is defined by clocks. The theory of relativity gave a consistent model of observable experimental results. Time first lost its absoluteness, then clearly gained the status of dimension. The findings of special relativity are summarized by the definition of the metric of flat space-time, the Minkowski metric, and the Minkowski metric relation properly, it's right there, to the sum of the coordinates of any arbitrary flat coordinate system in a flat space. And you have the speed of light turning the time dimension into a length dimension. Time travel should be possible, but this possibility suffers due to logical inconsistencies, paradoxes, and it is obviously unreal. We cannot travel in time, we cannot go into the past and kill ourselves without hitting ourselves hitting our proposal with a paradox. This is a wrong concept. So Giorgio is going to propose to solve the paradox problem by finding time, and his co-authors. We look for a fully explorable system of coordinates, Euclidean special relativity, a collection of various approaches to relativity in Euclidean space. The metric of flat space-time in ESR has the fully positive signature. Thus, the concept of space with four large space-like dimensions named four-space or hyperspace. From time to the hyperspace, in a common formulation of ESR, time is defined by this quantity, and what Giorgio has done is he's recast the time coordinate on the left in favor of putting the proper length on the right. And this begins to look like something that he missed, and this is called a pseudosphere. If you go on Google and you do a keyword search on a pseudosphere, you will find very interesting artwork that people have done over the years to give a representation of a pseudosphere. And that's essentially what this Euclidean special relativistic metric begins to look like here. And it's very unusual. Equation 1 is clearly the Minkowski metric with no modification. You have the coordinates, are the coordinate tau, x, y, and z are now the coordinates of the hyperspace, where tau is the proper time of special relativity. And that's essentially right. Tau can be recast at the proper time or proper length. Time is t is an integral local function of changes of the four space coordinates, dimensionally aligned by the speed of light. I think what he meant to say is dimensionally scaled. Time t exists if there is motion in the hyperspace. In the hyperspace, there is an invariant, the square of the four velocity, obtained by equation 1 by dividing out by dt squared. So we do that, and you define then the speed of light squared. In the hyperspace, all particles for which the Lorentz transformation is applicable travel at the speed of light, as you see given there. And for particles with velocity in the free space are equal to 0, like ordinary baryonic matter within space-time, it is the first term in the left member of equation 2 that is equal to the square of the speed of light. And the kinetic energy of the particles in the hyperspace coordinate system is the rest energy of the particles in special relativity. Nuclear energy can be interpreted as a conversion of kinetic energy along the proper time coordinate to motion and to photons in space-time. We generalize to the other three possibilities in which particles travel at low speed compared to the speed of light. In the three spaces, you'll have three spaces defined by these planes, tau xy, tau xz, and tau yz, as you see that Giorgio has delineated here. And they are all orthogonal for spaces. These three additional invisible space-times may manifest through gravity, possibly dark energy. A large-scale hyperspherical topology of the hyperspace may also model the expansion of the universe. It could be that he is looking at this in terms of truly the pseudosphere in a hyperdimensional cross-section is what he means by modeling the space-time expansion of our current cosmos. Photons of our space-time cannot move along the space dimension tau, while the respective matter universe runs away along tau with the speed of light. If the hyperspace trajectory of the photon intersects the trajectory of a suitable sensitive matter, then some computation is activated. Photons detected at the present tau have been emitted in a tau future space-time. In fact, for photons, we have the following relation there. with totality t squared equals 0. When matter increases its speed in a 3 space and approaches the speed of light, it shifts toward a local universe with different proper time, as shown by equation 2. Therefore, the parameters that must be controlled to start traveling in the hyperspace are the 3 components of the vector of direction and the 3 speed in any local system of coordinates in spacetime. So, according to Euclidean special relativity, we sit on one of the rectangles. We react to photons coming from rectangles more on the right and send photons to rectangles on the left. This is causality. So this is the motion that he shows there for that. Our material space-time consists of an infinite number of tau frames. Some are shown as contour lines in the figure. Tau frames are comparable to parallel realities. Particle P that you see located up there at the top in the cross-hatched field can reach a different space-time P prime with the help of a Lorentz transformation, a special orthogonal Ford group rotation. Curvature and gravity are described by the hyperspace refractive index in the simplified version of the theory of gravity in hyperspace. The refractive index is what holds the information for the computational model on a dynamic basis. According to many authors, the universe is a result of a large computation. Our reality is fundamentally memorized in 4 spatial dimensions, and the history time for our space-time is embedded within the proper time, tau. The underlying quantum computation creates a coordinate time and the motion in the hyperspace. T is the time of quantum mechanics, and it is a local parameter in our models that distinguishes the input and output of each elementary quantum computation. And the hyperspace holds the data structure of a highly parallelized optimized process. The propagation of all particles in hyperspace can be described similarly to the light propagation in spacetime. The refractive index of hyperspace is entitled to control the propagation speed. Propagation law is given above here, and I believe n is the refractive index, gravitational refractive index near mass is defined by equation 8. So basically that's a Schwarzschild. That looks like the Schwarzschild of the time component of the metric, which gives the inverse of the index of refraction. From an analysis that derives from the Schwarzschild metric, the propagation speed in the hyperspace depends on the gravitational field, with negative gm over r being the Newtonian potential, and it gives v equals speed of light times the absolute value of that quantity. For small masses with a low Newtonian potential and large distances, the presence of a point mass reduces the propagation speed with respect to that of light. Going very near to the point mass, the propagation speed is faster than light in the hyperspace. At the horizon, the propagation speed in the hyperspace is 0. The figure shows an encounter with the black hole in the hyperspace. I don't think this one's animated. So I believe what he's saying is you have a black hole appears here, you have a propagation far from the black hole. This is your local parallel universe at time 1, x, y, z, TL coordinates there. No propagation on the boundary, but you have a propagation far from the boundary. 4-dimensional trajectory of a traveler is, I believe, given here. So you have slower than the speed of light propagation there, and faster than the speed of light propagation on the inside. Black hole evaporates. You're now at a new time in a local universe. And I had trouble trying to pick up on that one, but not being in contact with Giorgio, I couldn't clarify that. The figure shows hyperspace travel using Schwarzschild-like metrics created with focused high-frequency gravity waves. So here he's showing a step-by-step process by using high-frequency gravity waves in order to allow you to jump FTL through his hyperspace. To travel FTL to a different point of the originating space-time, it is necessary to perform 2 FTL jumps, one in the proper time tau to reach the correct tau frame, and one in space of x, y, z in their spatial coordinates. During the trip, the running coordinate will always be the proper time. Traveling between parallel realities or parallel universes is also possible and may be easier. This is what is normally described as time travel in science fiction and tales based on GR. FTL travel in hyperspace, so that we'll press the space bar and watch the object leaves its space-time and it'll re-enter its space-time. So that's what apparently he's talking about in a step-by-step process. The collision or focusing of high-frequency gravity waves is a nonlinear process I think what that means is because we know in general relativity theory, we have indications that you could scatter gravity waves off of curved space, and they will then lead to nonlinear responses. It's not the same response as scattering electromagnetic field off of electromagnetic source, which is a linear response. So this is what he, I think, is trying to imply here. You will have nonlinear scattering because space-time is curved, and you don't get the same linear response as you do standard electrodynamic optics. All material particles can be described by wave packets or matter waves traveling at the speed of light in hyperspace. If it were possible to spatially, periodically modulate the refractive index of the hyperspace, we could easily obtain effects like the Bragg refraction and reflection of conventional wave optics. To do so, it is necessary to modulate the refractive index of the hyperspace with wavelengths of the order of lambda equals h over mc. That looks like that's the de Broglie with h Planck's constant. So this is the hyperspace de Broglie's wavelength of the transported particle as defined by Almeida. In the hyperspace, a gravitational wave is a propagating perturbation of the refractive index, and therefore it becomes a source of a new form of selective gravity. As a matter of fact, for a proton, the hyperspace de Broglie's wavelength is about on the order of 10 to the negative 15 meters, and for an electron, it is on the order of 10 to the negative 12 meters. And they are constant because all particles travel at the speed of light in Euclidean special relativity. High-frequency gravity waves produced by the nuclear generators of high-frequency gravity waves, which can operate at frequencies of 10 to the 24th hertz and wavelengths of 10 to the negative 16, 6 times 10 to the negative 16 meters, can be adopted to practically implement those effects. Fluctuations of the refractive index of 10 to the negative 10 are sufficient for practical applications at those wavelengths. A couple of synchronized generators at a distance apart far larger than the high-frequency gravity wavelength can be operated in an interaction mode, that is to synthesize interference patterns which can create directional hyperspace channels to the specific particles. Okay, he's showing an interference pattern which I'm not quite clear on what it is. Paul, do you know what the S word is?
No.
Okay.
He's got an animation.
Yeah, that's the space bar. Hit the space bar.
So here's the animation.
I think what he's saying is if I focus these gravity waves in front of me, this is the issue I was bringing up earlier this morning, I'm going to end up with a gravitational singularity, and that's going to cause some curvature and artificial gravity as well as some other effects.
Yeah, that's the way I understand it too.
Oops. I was trying to reproduce that, but when I had the slide,
He's also talking about the second figure where there's tunneling and other effects that have to be investigated.
All right, if an object A is set in a rotational state in 3 space, the result would be a reduction in speed along the proper time. The object A is therefore retarded in past configurations with respect to a nearby object that is not rotating. Therefore, object A should be seen to disappear by object B in our multiple proper time frame approach to Euclidean special relativity. Only that precise instant of object A will disappear, but other instances will appear, and at the limit of a light speed rotating object, object A, will not hypothetically see an external frozen scene comprising object B, as predicted by special relativity, but instead is a continuously changing version of the same scene. All the possibilities will develop. The hyperspace memorizes the last best persistent result in its memory. This is the point of view of the movie director. We are not making history, we refine it. Whatever kind of trajectory will object A perform in its slow motion proper time coordinate, the entire evolution of the trajectories of both objects will superimpose along tau and the space directions and very long duration travel made by object A will seem very short to object B. Light speed rotation of an object will allow a stop in this hyperspace. A possible configuration is described by the equation 10. The object is therefore detached from its original space-time in history. Finally, the rotating object might reorient itself and decelerate rotation to align its trajectory to that of another space-time. Then interaction would be possible. Conclusion. The hyperspace is the natural evolution and symmetry extension of general relativity space-time. Here the hyperspace is identified with the Euclidean force space of an extended formulation of Euclidean special relativity and the refracting four-dimensional optical space, four-dimensional, I think that's rotation.
4D.
F4DO.
Four-dimensional.
Most of the innovation resides in the interpretation of well-known equations, but without paradoxes. Results from general relativity and new original results from Euclidean special relativity has been proposed to enable space travel through the hyperspace. In the hyperspace, all particles normally travel at the speed of light. The new hyperspace propulsion technologies must only control propagation speed and the direction of travel. The end results are FTL travel and interdimensional or proper time travel. Schematization and travel diagrams for the new technology have been introduced. Thank you. Very good. So it's Giorgio is referring to the possibility of transiting into parallel hyperspaces by a special orthogonal rotation. The orthogonal rotation is, I think, defined by your velocity and your spatial direction, as if some sort of a velocity boost, similar to what Sonny White and I did last year with our deep rate reformulation of algebra program.
Let me add a comment. Basically, his point was that how do we deal with time? You can't go backwards into time into the past. You can't go forward into time into the future. So time is this very, very special coordinate system. How do we look at it? And what he's trying to do is change the whole context of how we evaluate time into certain characteristics that we can. And he's talking about how to go from one hyperspace to another.
Okay, John.
Yeah, it's too bad Giorgio can't be here. I would just like to make the comment that we are now living in an age where the special relativity paradigm, that there's no absolute time, is falling apart, because one of the paradigms of special relativity is you couldn't make an absolute speedometer. There were no absolutes. Everything is relative. But stay away from my daughter. It used to be, but we can now, using the cosmic background radiation, measure an absolute velocity by measuring its red and blue shift relative to kind of the center of mass of the visible universe. And this means all of these ideas about absolute time, traveling in time, have to be re-examined from what we used to. But I'll make one final comment. He talks about spinning, kind of spinning into hyperspace. And if you look at, I was looking at tachyons, because tachyons are now going to become more in vogue because dark energy can be explained as a tachyonic field. It turns out the imaginary number I can be written as a matrix, rather than just writing it down I, very mysterious, just the letter I. You can actually turn it into a matrix.
Well, I is the square root of -1, so that's a number. So how do you turn that into a matrix?
An identity matrix? Or what?
Well, you could, if you say you have an identity matrix, that's 1. And then you have a rotation matrix, a spin matrix. That's I. 1, it's 0 on the diagonals, and it's -1 on the bottom, and 1 at the corner.
But it's not the
Oh, that's
imaginary
what-
number.
But, well, you could. It turns out mathematically.
Think about it in moments of inertia matrix. Is that what you're saying?
No, that's more like a Dirac spin matrix.
It's like a Dirac spin matrix. You can write a kind of Dirac spin matrix for I itself, and it behaves mathematically just like I. And it's a spin. It's as if what is imaginary matter? It's matter that's spun. At least that is one mathematical model. So, there's a
Tim,
connection.
that's a kind of question?
Yeah, I was wondering the way that he treats time in this, and I know that mathematically you can plug time into an equation and juggle around just like any of the other dimensions, but it seems like he's trying to metricize it, I guess, just like he would, any of the spatial dimensions. And it just seems like that is never, I don't know, in this context, may work mathematically, but chopping up into a series of, infinitesimal moments, I don't think is the right way to do it.
I don't think he's doing anything wrong. He's just redefining time as a parallel universe slice. And that's essentially what you do in general relativity anyway. Time has no definition in general relativity. What it is a slice of geometry that evolves. And this is similar. And I think he's laying it out, but in a Euclidean sense. He's
okay.
working from a flat space perspective. Any other questions or comments? There's Andrew.
Quick one about the usual engineering implications, experimental predictions from theories, or any sense of that in Giorgio's paper?
Andrew, I can't even hear you from over here, so the acoustics is bad. Unless Paul wants to answer that. Or
I'm sorry, I didn't hear you.
Experimentation, is there any experimentational ways to test this?
Well, what you're asking is, how do I go from one dimension to another? Is there any experiments that validate I went from one dimension to another? The only argument we could say is we talk about it theoretically until the cows come home. A paper that Bob and I presented several years ago at AIA, we were talking about jumping to other dimensions. And we found out that here we live in a four-dimensional world, but there was some research that indicated gravity was fifth dimension, which means maybe we could use gravity to go into another dimension and open a door. Now, the other point that my friend over here is making about I is so emphatic. If you look at some of these equations, and you're going to see it when I give my last paper, I need an imaginary number. And the thing is, here's a physical quantity multiplied by an imaginary number. What's the rationale I could use for that to describe it physically? Well, the only rationale I have is it's coming from another dimension beyond the four space that we're in. I mean, it's a coward's way out, but it's the only thing I could suggest. So, as far as I can suggest, when he did his paper, he was talking about a photon coming in from another hyperspace, another four-dimensional space, and also photons leaving your four-dimensional space to go to another one. Well, how do you measure that? I don't know how, and he doesn't tell you how in the paper. So this would be an area where obviously we need to do some more work on to understand what's going on. And if we're going to talk about space travel, and even, warp drives or wormholes, do we really understand what we're saying here? And this is why I raised that point earlier about focusing gravity waves. What's going to happen at that focal point? If you have a large strength of gravity waves, you're going to have space-time curvature. Something's got to happen. So we need to think these things out and quantify what it really means. And hopefully, we can have some of those answers next year.
I'll just make one comment. When you study quantum mechanics, you find that you can't get rid of the I. No matter how hard you try, you can't write equations for quantum mechanics without that I sticking out someplace. And so, in a sense, quantum mechanical tunneling is kind of analogous to what he is describing. The idea that electrons can go through barriers, can climb over, tunnel under barriers that they shouldn't be able to get through, is sort of analogous to the engineering question. We may be seeing nature in a way of doing this already.
It's an interesting speculation that he's been gelling on this since last year. John, you're the session chairman. Do you want to go ahead and take
Why
over?
don't we take a 5-minute
next
break?
talk?
I think we should take a 5-minute break.